America's greatest industrial nation, today more than ever before in history, turns to its industries to lead the way. Make it better, make it cheaper, make it faster. That is the American tempo, the demand of the American people. Ever since the wagon train started across our western prairies 100 years ago, ever since the horse and buggy days, this American demand for speed, for quality, for low-cost production has been answered without fail by the men and women who are in industry. Industry is manpower. Industry is money. Industry is men and machines. Industry is time and energy. Industry is light. Light keeps the wheels of industry turning during the day. Light makes it possible to change the often wasted hours of darkness into hours of useful production. Light helps make it better, helps make it cheaper, helps make it faster. It is light that steps up the American tempo. Light, lots of light, reduces errors, avoids waste, saves time and materials. Light, lots of light, reduces eye strain, reduces headaches, saves energy, builds up health and cheerfulness. And on the road, better street lighting and sealed beam automobile headlights might have prevented this accident. Everywhere in every business, in every walk of life, better light speeds up work, saves time, saves energy. In many machine shops, better lighting has increased production as much as 5%. In other factories, better lighting has increased output by more than 8%. In shipyards, floodlighting helps the night crew turn out as much work as the day crew. Better lighting helps put entire plants on a 24-hour schedule. If better lighting increased production by only 3%, that would mean 300 million more man-hours per year in war industries alone. That's the man-hours needed to build 43,000 more tanks, or 12,000 more training planes, or 2,400 more bombers, or 100 more destroyers, or 11 more battleships. Why can we work better and faster with good lighting? Well, let's go into the movie studio where this picture was made and see what lights can do. See that vase of flowers on the table? The light's kind of bad, isn't it? And you can't see the flowers very well. But hit those flowers with a couple of good lights and see what happens. Looks bigger, doesn't it? And it stands out from the background. When we increase the amount of light on an object, we see it more quickly and we see it more accurately. So we save time, we save energy, and we save eye strain. Dedicated to the science of better lighting, hundreds of men and women at Nela Park, Cleveland, Ohio, are helping America do it better, do it cheaper, do it faster by constantly improving the design and use of electric lamps. In these vast research and experimental laboratories of the General Electric Company, the American tempo is itself applied to the manufacture of Mazda lamps. Within these buildings, the men and women of Nela Park are themselves seeking ways to make Mazda lamps better, to make them cheaper, and to make them faster. Modern, high-speed machinery designed at Nela Park turns out better lamps of uniform quality and turns them out at lower cost. Before these machines were developed, lamps were made almost entirely by hand, a slow, expensive, laborious process. Let's look at the record. In the year 1907, the average 60-watt, 120-volt Mazda lamp rated 450 light units and sold for around $1.75. By 1920, the light units had increased to about 575, and the price had gone down to 45 cents. By 1940, the light units had increased to over 800, but the price had gone way down to 13 cents. And that's the American tempo at work. Better, faster, and cheaper. 10 different parts make up an incandescent lamp. There's the glass flare, 2 lead-in wires, a glass exhaust tube, 3 molybdenum support wires, a tungsten filament, a frosted glass bulb, and a metal base. Those 10 parts are fed into the machine separately at various points. They go round and round like the music in Yuba's tuba, and they come out here finished lamps. Don't ask me how, but I'll try to show you later on. Meanwhile, there's more to making a Mazda lamp than meets the eye. Mines all over the world supply nickel, copper, tin, tungsten, manganese, and other metals. Wire-making factories work the metals into wires and filaments in literally thousands of shapes and sizes. Special factories turn out millions of metal bases every day. Chemical plants reclaim the necessary gases such as nitrogen and argon from liquid air. Argon gas is one of several rare elements found in the air we breathe. These huge control panels guard the purity of the gases used in Mazda lamps. For the scientists of Nela Park found that tungsten filaments burn brighter and longer in a mixture of pure argon and nitrogen. Glass furnaces operate day and night to produce the several different articles of glass required in every lamp. Here is an amazing machine that turns out many thousands of glass bulbs every hour. It operates steadily day and night without stopping, making them faster and making them cheaper to the tune of more than 1 million glass bulbs every day, all exactly alike. Not so long ago, bulbs were made by hand, or to put it more accurately, by huffing and puffing. We hope he makes it eventually. But look at them now, bulbs by the hundreds, made and frosted on the inside in a matter of seconds. The frosting reduces glare and diffuses the light. The bulbs are then given a number of rigid inspections. Those with the slightest flaws are discarded. Following Uncle Sam's conservation policy, the glass from the broken bulbs is reclaimed and used again. And to make sure that you buy only perfect lamps, more than 400 different tests are given to individual parts and finished lamps. Here, the girls are testing the bulbs for imperfections. The flare is another important glass part, as its wide mouth forms an airtight area for the nitrogen and argon inside the bulb. Time was when the flares were also made by hand, but that was too slow for the American tempo. Nowadays, hundreds of flares are made in a few hours from long tubes of glass by a special machine that heats the glass, forms the flares, and cuts them off one at a time, but quickly, in exactly the right shape and length. Amazing, isn't it? But it isn't half as amazing as the story of the filament, the tiny coil of tungsten wire that is the heart of every Mazda lamp. Literally thousands of filaments are made from one short bar of tungsten. How? Well, let's go down to the wire works and find out. When the tungsten ore comes from the mine, it is made into powder, and the powder is pressed into bars. By repeated hammering in special machines, the tungsten bars gradually become long, thin rods. Watch. The rods are pulled through diamond dies until they become wire fine enough and pliable enough for even the smallest filaments. As much as 5 miles of filament wire are often drawn from one 18-inch tungsten bar. That's stretching it pretty fine, finer in fact than a human hair. Pull a hair out of your head and look at it. Kind of thin, isn't it? Well, this piece of filament wire is only 1/3 the diameter of a human hair. So thin that you can't measure it. You've got to find its diameter by weighing it, which is what this young lady is doing. It weighs some fantastic fraction of a milligram, which shows up on this dial. If the weight is correct, the diameter must also be correct. But the wire is not yet ready for use. Making it better is still part of the American tempo. Before any run of filament wire is approved for production, sample filaments are made and given life tests in sample lamps. The burned out filaments are carefully checked. Not until the sample filaments have passed these tests is the wire allowed to go into finished lamps. Last year, more than 25 million filaments were rejected, but don't think they were wasted. Most of them were melted up and came back again for another try. Not so many years ago, most lamps used long, straight filament wire festooned around supports by hand. Some lamps are still made that way. But one of General Electric's brilliant scientists discovered that a coiled filament wire operating in a gas-filled bulb would give more light and fit in a smaller area like this veteran of 25 years ago. And another engineer designed a machine to coil the straight wire. But that isn't all. Another young genius discovered that coiling the wire a second time gave even more light in a smaller space with the same amount of current. And still another GE engineer designed a machine to do the trick. Nowadays, most of the large production Mazda lamps use the coiled coil filament for better light at lower cost. Here is the coiling action in slow motion, showing clearly the second coiling of an already coiled wire. This astonishing machine turns out finished coiled filaments ready for use. But now, the problem is how to get that filament inside the glass bulb and make it light. Magic? Almost. But here again, the most amazing machines of all do everything the human fingers can do, and do it better and cheaper and faster, making them all exactly alike. Individual parts are fed into this ingenious product of the machine age one by one. The assembly is built up progressively as it moves around the machine. The assembly at this point looks like this. The narrow end of the glass flare must be sealed shut to hold the parts in place. So, the end of the flare is heated, hot enough to mold, but not hot enough to melt. Then a couple of clamping jaws come in at just the right moment and do their stuff. Neat and fast, you'll agree. But here is our friend ancient history again. The flare used to be sealed by hand. Monotonous, isn't it? Oh, hum. Well, let's get up to date. There, that's better. Machinery fascinates me somehow. But there's a catch in this whole thing right now that has to be corrected. Having sealed the flare shut, we have also shut off the exhaust tube and eliminated any way of getting the nitrogen and argon gas into the bulb later on. So we have to blow a hole in the flare to open up the exhaust tube. Here it is in slow motion. Watch. Yep, there she blows. And here's a very interesting thing. If anything goes wrong on this machine, the light lights, bells clang, sirens scream, whistles roar. What? Oh, hold everything, fellows. Oh, sorry, folks, my mistake. Go back to the firehouse, boys. Only the light lights. And the supervisor looks for and corrects the trouble so that little or no production time will be lost. Now we come to some real magic. Suspending the filament on the lead-in wires. First, the lower end of the exhaust tube is heated and a button formed. Support wires are inserted in the button, which holds them firmly in place when it cools. The filament is laid across the hooked ends of the lead-in wires, and the ends of the lead-in wires are clamped around the filament, firmly securing it in place. The support wires are also clamped in place. Years ago, when lamp making was just plain hard work, the filament was cemented to the lead-in wires by hand. But that was before lamps were cheap enough so you people could buy them by the millions. Nowadays, an almost human mechanism picks up the filament automatically, suspends it on the lead-in wires, and firmly clamps it in place. And it happens so fast you can hardly follow it with your eyes. At this point, the filament assembly looks like this, and is ready to be sealed inside the glass bulb. To save time, the assemblies are transferred mechanically to the operator of the sealing machine. The filament assemblies are placed in the sealing machine by hand, and a glass bulb fits down over each one. The familiar GE Mazda identification is stamped on the inside of the glass bulb so that it cannot be tampered with. In this machine, the filament assembly is sealed tight inside the bulb and nitrogen and argon gas injected through the exhaust tube. Here's how. The glass is heated and the wide mouth of the flare and the neck of the bulb are sealed together by molding them into one solid piece of glass. In the olden days, this was done by hand. But here again, The mind of man designed a machine for speed and better quality. And here it is. Sealed tight in a matter of seconds and ready to have the air exhausted and the gases shot in. This is done on a lower row of the same machine to save time, because if the glass cooled, it might suck in moisture. And here's one for Ripley. The equivalent of just one drop of moisture would ruin 100,000 lamps. Here the air is drawn out of the lamp and the gas is injected. If we could just climb inside this airtight machine, here's what we'd see. First, air is withdrawn through the exhaust tube. Then at the next opening, a mixture of nitrogen and argon gas is injected. This cycle is repeated a number of times to ensure that every lamp is free of air and contains just the right amount of gases. Then the exhaust tube is sealed off, making the interior of the lamp completely airtight. Not so many years ago, lamps contained a sharp, dangerous tip at the top of the bulb. Remember? That's where the exhaust tube used to be sealed off. But with the development of modern machinery, it became possible to seal off the exhaust tube in a part of the bulb that goes inside the base. Clever, eh? The bases are fitted to the bulbs by hand. Too fast for you? Well, let's see if we can get the young lady to slow down a bit. There. See how it's done? Those are the lead-in wires she's positioning. But we're still not finished with machines. The bulb must be securely cemented to the base, and this is the machine that does it. Heat again does the trick, and when the base cools off, that bulb is stuck in there for keeps. After the lead-in wires are soldered to the base, the lamps are test lighted right on the machine. Only 13 minutes have elapsed from start to finish. Yet in those 13 minutes, this one machine unit has produced more than 100 lamps, one as nearly like another as human ingenuity and modern machinery can make them. The operator tests every lamp as it leaves the machine. If one doesn't light, the operator tests it against a pinpoint of light, and shadows reveal whether all interior parts are intact and properly placed. Hundreds of tests are made to be sure that you buy only perfect lamps. And to double-check the GE tests, additional tests are made under the direction of an independent testing laboratory. Let's look at some of these independent tests. Another light test. A seasoning test at a voltage 20% greater than the lamp's rated voltage. A bump test, equivalent to dropping the lamp on the floor. If it lights after that, it must be okay. But that isn't all. Is it the correct length? Will it fit into standard sockets? Are bulb and base securely cemented together? Now, here's an interesting sign. But movie producers are privileged people, so let's go in. This is General Electric's own testing laboratory at Nela Park. Here's a vast room where sample lamps of every type are on light test. They're burned until they burn out, and periodic checks are made of their characteristics. Uh-oh, balloons? No, photometers, where the lamps are tested after burning a certain number of hours on the life racks. The young lady makes a complete case history for what might be called the life of a Mazda lamp. The lamp is then returned to the test racks for additional burning and comes back here for more readings later on. And you've all ridden on trains, trolley cars, and maybe on the subway too, without thinking about the licking train lights have to take. So here is a machine which simulates the vibration of a train, including a gentle little gadget which reproduces the action of a car with a flat wheel. And this big Bertha drops the lamps various distances as it revolves. This is to see if the lamps can take it. Some sturdy souls even survive the big drop at the finish. Yes, modern high-speed machinery turns out better lamps of uniform quality and turns them out at lower cost. Thanks to the men and women of General Electric, who have designed more than 9,000 different types of lamps required for hundreds of necessary lighting purposes. Lamps that kill germs for better health in home, office, and factory. Sealed beam headlights for automobiles and airplanes. Grain of wheat lamps, which help doctors perform modern miracles. Small 1,000-watt mercury lamps for powerful searchlights, giving many times more light than the lamps formerly used. Black light lamps that cause certain materials to glow in the dark for better visibility. For instance, the instrument panel of a bomber. Lamps for literally 1,001 purposes. Lamps for photography. health lamps giving ultraviolet or infrared rays, flashlights for every conceivable use, lights for every form of transportation, lamps for the use in the bowels of the earth and under the sea, floodlights that turn night into day for construction, for industry, for transportation. And now, the newest development in the science of lighting, fluorescent lamps for homes, for offices, and for factories. The closest approach to natural daylight ever created scientifically, with the added advantage that fluorescent light is cool light, light that gives off relatively little heat, the kind of light for which man has searched for many centuries. The secret was discovered in rocks containing certain chemicals that absorbed ultraviolet rays from the sun during the day and glowed after dark. Ways were found to manufacture these and other chemicals in powder form. The powders used in fluorescent lamps, for example, glow brightly when exposed to certain ultraviolet rays, but do not have any afterglow. The inner walls of the long glass tubes are coated with these powders. A small drop of mercury is placed in, and specially treated coils are placed at both ends of the tube. When current goes through the coils, the mercury vaporizes and establishes an arc between the coils, thus creating ultraviolet rays, which cause the chemical coating to glow. While the principle is simple, it has been more than 300 years since fluorescent rocks were first discovered in Italy. From this discovery, science today has developed the most ideal type of lighting ever known. Lighting that has, as one usage, speeded up the tempo of production in many of America's giant industries. Lighting that gives 3 times the candle power from a given amount of current. Lighting that practically eliminates annoying shadows. Lighting that helps save eyesight because there is less glare and less eye strain. Lighting which, by changing the chemical composition of powders, can be made to glow in a variety of colors. So, better lighting carries on our American tempo, always faster, always striving for new and better ways. Production, more production, faster production. That is the demand of the American people, and that demand will be met. In meeting that demand, better lighting will play a vital part. Proper lighting, powerful lighting, lighting that speeds up the tempo of production. Lights that save time, lights that save energy, lights that save man-hours, lights that safeguard the eyes of youth, lights that preserve the usefulness of older eyes, lights that extend the hours of productive work, lights that keep the wheels of industry turning faster, 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 lights that will help guide industrial America to victory, lights that will help guide the world toward freedom and liberty and peaceful happiness. For this, too, is the American tempo.